Assalamualaikum warahmatullahi wabarakatuh. So this is our title, which is Green's Theorem. So in our team we have Ahmad bin Muhammad Gamal, Mirza Akmal Hakim bin Muhammad Rizal, Zahira binti Jamaluddin, dan me, Nur Alia Fahra binti Muhammad Yusuf.
For the introduction, Green's theorem is applied to integrate derivative in a certain plane. Using this theorem, a line integral may be turned into a surface integral or a double integral. This theorem is one of calculus' four fundamental theorems. Green's theorem is similar to Stokes' theorem in that both are founded on the notion of connecting microscopic and microscopic circulations. Let C be the positively oriented and simple closed curve in a plane, and D be the region circumscribed by C for the formulation of Green's theorem. Then L and M are functions of x and y defined on the open area, which include D and have continuous partial derivative, and the Green's theorem will be written as below.
So now I'm going to tell you about the problem statement. By using the Green's Theorem, evaluate where C is shown as above. Integrate at point C, x squared y squared dx plus bracket yx cubed plus y squared close bracket dy. Firstly, we consider C as the curve counterclockwise and oriented triangle with the vertical point at 4, 4, 0, 0 and 9, 2. So next, the equation of line through the points 4, 2 and the point 0, 0 is y equal to 1 over 2x. Next, the equation of line through the point 4, 2 and 4, negative 8 is x equal to 4. Lastly, equation of the line through the points 0, 0 and 4, negative 8 is y equal to negative 2x. So the answer is given like the pictures that shown in the slide.
Next, I will continue the problem statement that compute y squared dx plus 3xy dy, where C is the counterclockwise oriented boundary of upper half. Unit this D that we derivative 3y minus 2y equal y.
So just now we stated that the problem statement is by using the Green's theorem, evaluate the integral C x squared y squared dx plus open bracket y x cubed plus y squared close bracket dy. As it stated that C is oriented in counterclockwise, so we let the equation become the negative equation, and then we let P is equal to x squared y squared, and then Q we let equal to y x cubed plus y squared. Next, we want to use the Green's theorem, so we make it to double integral, and we do some partial differentiate of x and partial differentiate of y. When we want to the partial differentiate of x, we use the equation on Q, and when we want to partial differentiate of y, we use the equation in P. Then we get the answer is double integral yx squared dA. Next, using the point given, which is x is at 0 and 4, so we need to find the point of y, which is we get negative 2x and 1 over 2x. So we put the point in the double integral. So we let the integral at 4, 0 and integral 1 over 2x and negative 2x yx squared dy dx. We use the dA in dy dx because it is only line integrals, not oriented in the circle motion and so on. First, we integrate in the inside first, which is dy. So we get the 1 over 2 y squared x squared, and we substitute the point 1 over 2x and negative 2x. Then we integrate again with in the dx, and we get negative 15 over 8 x to the power of 4 dx uh, we integrate it at point 40, and then we get 3x to the power of 5 over 8. So the answer is negative 384. Next, we want to compare in the Maple software. So we put the Maple command, which is, so first we define the equation of P, which is P is equal to x to the power of 2 and multiply by y to the power of 2. Next, we define the equation of Q, which is yx cubed plus y squared. Next, we get the output is P is equal to x squared y squared, and then Q is equal to yx cubed plus y squared. Next, we differentiate partial differentiation of y using the equation of P. So we get 2x squared y, and then we did partial differentiate of dx using the equation of Q. We get the 3x squared y. Next, we find the C point, which x is at 0, 4, and then the y is at negative 2x and 1 over 2x. So we do the double integral of yx squared dy dx and use the point that we find at C before. So we get the answer same as the manual, which is negative 384. So that we can conclude here that by using the Green's theorem, we can see the manual way and the Maple software have shared the same answer, which is negative 384.
Okay, Assalamualaikum and hi, my name is Mirza Akmal Hakim bin Muhammad Rizan and my ID number is 2020492686 and I will present for the case study number 2. Okay, in this case study, the question is asked to compute the equation where C is the counterclockwise oriented boundary of upper half this D. Okay, for the first thing first, we will get from the equation is x is in between negative 1 and 1 and y is from 0 to set 1 minus x squared. Okay, from the equation we can get equal to double integrate and this one and equal to double integrate y dA. So for the range we can get from 1 minus set 1 minus x squared from 0 to set 1 minus x squared y dy dx, and for the second one is negative 1 to 1. Okay, after that, after we settle the integration, we can get the answer is 2 over 3. And we go to the Maple solution. On the Maple command, we must write restart equal to with student vector calculus to access for this equation because of we cannot proceed if we didn't write student vector calculus, and then we identify P and Q, then we integrate P and Q and we get negative 1 until 1 for x and 0 to set 1 minus x squared for y, and then we write down the equation from what we get from x and y, and then the answer will the output will get 2 over 3, and we can get for R1 and R2 this R1 and R2 we can get for the graph that automatically uh, made by the mapper. That's all. Thank you.
The conclusion, I will conclude that Green's theorem can be used to calculate line integrals of arbitrary curve by closing with a curve C and subtracting the line integral over the x segment. Green's theorem is example of statement that the integral of two-dimensional conservative fields over a closed root is equal to 0. This study shows that Maple software works perfectly with Green's theorem by given the same answer with manual calculation. That's all from us. Thank you.